Hello, everyone. Welcome to today's webinar. Before we get started, we would like to review a couple of items. First, we welcome your questions during today's webinar. Please use the Q&A button located at the bottom of your screen to ask any questions you might have at any time during the broadcast. And we will answer your questions at the end of the presentation. Also, today's webinar is being recorded. A link to the recording and the slides will be sent out via email following this event. The webinar itself is scheduled to take about 30+ minutes long, and it will be followed by the Q&A session. So let's go on and start with the webinar. Let me introduce myself. My name is Benny Alevi, and I lead the storage development team at ScyllaDB. I've been working on operating systems and distributed file systems for over 20 years. Most recently, I led software development for GSI technology, where we provided a solution for deep learning and similarity search using in-memory computing technology. Rafael, please introduce yourself as well.
Hi, everybody. My main areas of interest is distributed systems and operating systems. And in ScyllaDB, I've been working with SSTable handling, compaction strategies since then. And that's it.
A little bit about the company, ScyllaDB. We are behind Scylla, the real-time big database. Scylla is a drop-in replacement for Cassandra, but with 10x the performance and very low tail latency. We're available on the cloud and on premises with both an open source version and an enterprise edition. And if you haven't already, I encourage you to try Scylla, of course. And on to today's agenda. We will start with an overview of log structured storage that is used by Scylla. And we'll describe the fundamentals of compaction and also the existing compaction strategies in Scylla. Then we will present our innovative compaction strategy, incremental compaction strategy, by describing the problem it's about to solve. And we will give an overview of ICS in a nutshell. And finally, we'll show you some numbers where we compared ICS to STCS using right workload. And we will go over some future directions we are working on. And finally, we can answer your questions. So again, feel free to write these questions up while we're talking. Okay, to start our introduction, let's talk a little bit about log structured storage. Scylla, like Cassandra, stores data using a log structured method. Any changes to the data that we call also mutation fragments are first recorded in memory and are stored in parallel also on disk in the commit log. These buffers that are called memtables are flushed into SSTables. The name SSTable stands for sorted strings table, and it stores a set of mutation fragments that are sorted by their partition key and clustering keys. Note that there are no tables storing a static view of the database like other relational databases. All the data is essentially stored in these SSTables. When we want to read a particular data item, reading it requires reading all the SSTables that may store any part of it. And then those parts are merged together. They contain live mutations, need to be merged from the read results, and then they comprise the final version of the data. The SSTables themselves are immutable, i.e. they are never updated in place. They are written once and eventually they are deleted. Therefore, those updates, those mutations, accumulate over time in the SSTables. And we have to merge the SSTables together and keep only the live data to avoid running out of space. And this is where compaction comes to the rescue. Let's describe the fundamentals of compaction and note the diagram on the upper right-hand side. So the first thing that compaction does is to select a set of SSTables to process. This selection algorithm is based on the compaction strategy. So different strategies may select different set of SSTables to process at any given time. Then compaction reads this SSTable and it writes the compacted output, where it can eliminate any overwrites that happen between the selected SSTables. It can also eliminate any data that was explicitly deleted, and also data that expired over time based on its time to live, or TTL field. Eventually, when the output SSTable is sealed and safely stored, so when we store it on stable storage, the input SSTables can be finally deleted. And this is an important thing to mention, that compaction requires temporary storage. So the output SSTable is being written while the original input SSTables are still on disk. And these SSTables must not be deleted until their compaction completes. Otherwise, there are corner cases where data can be resurrected if we crash in the middle and delete some of the SSTables and not all of them. Let's dive a little bit more into the details. And we prepared a little animation that will depict different kinds of mutations that we compact. So first, let's look at A and A prime. A in this case is overwritten by a new version of the cell, marked here as A prime. In this case, we can eliminate A and just copy A prime into the compaction output SSTable. B, in the example, is newly written. It contains new data and obviously needs to be copied into the output SSTable. C, in the example, is deleted by not C, which is a deletion marker, or otherwise called a tombstone. In this case, we can eliminate C, but we still need to keep the tombstone until it expires. So not C is copied into the output SSTable. Similarly, the input SSTable may contain a live tombstone that has not yet expired, that also needs to be copied into the compaction output SSTable. Those tombstones that expired their garbage collection timeout can finally be eliminated. So note here that the tombstones are kept around for GC grace seconds until they are garbage collected. And this is done to prevent data resurrection. Next part of the introduction will describe the legacy compaction strategies in Scylla. First, let's talk about size-tiered compaction strategy. In short, called STCS, this is Scylla's default compaction strategy, and it was inherited from Cassandra. This compaction strategy organizes SSTables into tiers, where in tier N for examples. All SSTables are roughly the same size, and they are k times bigger than the SSTables in tier n-1. And this parameter k corresponds to the mean threshold configuration option. For example, when we compact k SSTables in tier n, a single SSTable is created. Now, it may be as large as the union of all k SSTables if they contain mostly unique data and barely overlap. And then it is moved up to the next tier. In other cases, it may even become much smaller if the input SSTables have lots of deletes or lots of expired data. And in this case, the output SSTable might be moved to a lower tier. Let's talk a little bit about STCS's space amplification. So first, STCS results in a low number and a logarithmic in the size of data, low number of SSTables. And data is copied during compaction a fairly low number of times. This means that STCS has low write amplification. However, we note that STCS requires that the disk be substantially larger than a perfectly compacted representation of the data, i.e. when all the data is concentrated in one single SSTable. This ratio of the amount of disk space required for the compaction strategy versus the size of the data is called space amplification. The main factors for space amplification are first, the accumulation of updates and deletes across the different tiers. And note that these updates and deletes cannot be compacted unless they happen to be in the same tier, because STCS is compacting SSTables only if they reside in the same tier. So if the updates happen to be in different tiers, they cannot be compacted by STCS. And then the temporary space requirement for STCS is also very high, in particular for compacting the highest tier. So if you imagine on the lower right hand corner that all the data now resides in the largest SSTable in the highest tier, in order to compact it, STCS needs to create a new SSTable that will contain only the live data that's currently in this SSTable, and it might be pretty much at the same size of this SSTable. And in this case, temporarily, STCS will need twice the amount of disk space to hold both the original copy of the data and the compacted SSTable output. We will later see this temporary space being used when we show the case study and show you the actual graphs taken from STCS. Okay, in contrast to STCS, we have the leveled compaction strategy, called LCS for short. First thing that we note about the leveled compaction is that it replaces those large SSTables, which are the staple of STCS, by runs of small, fixed size SSTables. The size of these small SSTables is pretty much determined by the size of the mem table. So in level 0, LCS stores all the new SSTables that were recently flushed from the mem tables. As their number grows, causing reads to slow down, LCS's goal is to move SSTables out of this level onto the next levels. And each of the other levels, level 1, level 2, and so on, is a single run of an exponentially increasing size. So level 1 will contain, for example, a run of 10 SSTables, while level 2 will contain a single run of 100 SSTables. Next level will contain 1,000 SSTables, and so on. So it happens that LCS results in high write amplification. Compaction is triggered whenever some level I consists more than 10 to the I SSTables. So for example, if level 1 will contain 11 SSTables instead of 10, LCS will immediately recompact it to get back to 10 SSTables. How does it do it? It picks one SSTable from level I. That SSTable will have a size X, for example. So it's being picked up for compaction. And then it finds roughly 10 SSTables in the next higher level, I+1, which overlap with this SSTable. And then it compacts them together against the one input SSTable, and it writes the resulting run that size is bound by 11x. This is the one SSTable that we compacted from level I, plus the 10 SSTables from level I+1, times the size of the fragment, which is x. We write the resulting run to the next level. So here, for example, one SSTable from level 0 is compacted against 10 SSTables from level 1, resulting in a new run. Now this may cascade, causing level 1 to be compacted, and then we will pick one SSTable from level 1 and 10 SSTables from level 2 and compact them together, and so on. So this process requires a lot of overwriting of data. We call this write amplification. So while LCS limits space amplification by being very aggressive in compaction, it results in much higher write amplification, as data updates need to be frequently compacted along with unchanged data that is merely copied over and over again to new SSTables. Okay, it's time to present our new compaction strategy, incremental compaction strategy. Let's start with describing the problem that we are trying to solve. We observed problems with the legacy compaction strategies. So STCS has high space amplification, as we saw, and at the same time, it has relatively low write amplification. In contrast, LCS has high write amplification and relatively low space amplification. So we wanted a compaction strategy that would basically benefit from both approaches. And then came the idea of incremental compaction strategy. In a nutshell, ICS was originally called hybrid compaction strategy, since it's based on both LCS and STCS. ICS is currently based on the size-tiered compaction strategy, and while sharing its low write amplification, it reduces STCS space amplification. It does so by borrowing the concept of SSTable runs from LCS. By doing so, ICS has reduced the temporary space requirements of size-tiered compaction strategy. It does so since individual small fragments from SSTable runs are compacted and are freed early as soon as they are exhausted. And we'll go over the details of that right now. Note that ICS still avoids LCS's worse right amplification, since it follows the same flow of STCS size tiers. We merely replace the increasingly larger SSTables depicted here in gray on the left side of the diagram. We replace those with increasingly longer SSTable runs depicted in blue on the right-hand side. So each run corresponds to the same size SSTable that STCS would create. It is just being divided into a set of smaller fixed size SSTables. So what are these SSTable runs? A SSTable run is a sorted set of SSTables with non-overlapping token ranges. Those small SSTables are called fragments. And each SSTable run is essentially equivalent to a large SSTable that is split into several smaller SSTables. Remember that SSTable is called so since it contains a sorted string table. So essentially it starts its life as a sorted array of rows. And here in this diagram, we can see the SSTable having a number of partitions called A, B until Z. And then each part can be stored in a separate SSTable. And those are shown as linked together into a single run. Now, since fragments are disjoint and sorted with respect to each other, we can scan these runs and compact them incrementally, fragment by fragment, while deleting the exhausted SSTables as we go. So in this example, ICS starts with the first fragment of each run, shown here in capital A and lowercase a. And then it compacts only these two fragments together into the output fragment, denoted here as A plus A. When the output fragment is sealed and flushed to stable storage, ICS can now, in essence, can delete the first fragments of the compacted runs and move on onto the next fragments. To summarize, let's compare the properties of ICS with STCS and LCS. First, space amplification. We realized that it's very high in STCS, and it's highly improved in ICS by using SSTable runs that reduce mainly the temporary space requirements of STCS. In LCS, however, we have even lower and bound space amplification. As for right amplification is low in STCS due to the exponential SSTable size. And this property is kept in ICS since we essentially copy the same tier structure, just implement it with SSTable runs instead of large SSTables. However, right amplification is very high in LCS that trades space amplification for write amplification. It's doing very aggressive compaction to keep space amplification low, and that costs it with very high write amplification. As for the number of SSTables, which may also be a factor, this number is low in STCS because of the way it organizes the SSTables into tiers, and by keeping the SSTables very large. The number of SSTables is increased in ICS because we divide these large SSTables into a constant sized SSTable fragments. So we will end up with more physical SSTables on disk. In LCS, since it uses a small fragment size, typically the size of the mem table, we end up with many SSTables on disk, which might hurt performance due to the increased metadata overhead required to keep track of many SSTables on disk. With that in mind, we can move on to present our case study, where we will show test results comparing ICS to STCS under write workload. So, Rafael, on to you.
Hi, everybody again. So the main reason behind this graph is to analyze the compaction strategy behavior, the disk usage behavior of those compaction strategies over time. The graph in the screen, it was generated by sampling disk usage over time. You can see it's composed of 3 steps. The first one being write-only workload, the second one being overwrite, and the final one being major compaction. So the basic idea is to analyze, to verify how the compaction strategies behave when giving a different set of workloads. So we want to see how much ICS was improved over STCS. So the first step is basically about writing data to the database. It's 500 gigabytes. And you can see that unlike STCS, ICS has no disk usage spikes at all. You can see that it has much more predictable disk usage because it, like Ben explained, it's able to release the disk space as compaction proceeds, unlike STCS. Because like Ben explained, STCS has to wait for compaction to complete before releasing the SSTables involved in compaction procedure. So that's how it allows ICS, this incremental compaction approach, to reduce the disk usage and provide the user with much more predictable disk usage for a different set of workloads. So when the next step is overwrite, so we keep writing the same data over and over again. And you can see that overwrite requires more from the database. And in STCS, you can see those huge spikes because it has, like it was explained, has to wait for compaction to complete. And even though it's like the worst case scenario for both strategies, ICS is able to release disk space and provide the user with more predictable user space. You can see that it has no spikes at all. It grows like STCS, but the disk usage peak doesn't grow as much as STCS. And the final step, which is major compaction, it's used very often by users to like a measure to release disk space, like a hard measure. This procedure is basically about compacting all the SSTable together. As a result, you want to get rid of duplicate data, expired data, and so on. ICS, unlike SCCS, is able to provide the user with a much more predictable disk usage again, because it's able to release the SSTables as the major compaction proceeds. So it takes all the SSTables as input to compaction, and as it finishes writing one SSTable fragment, it's able to release it immediately. Unlike STCS, because STCS, Side-Steered Compaction Strategy, it doesn't have the incremental compaction approach. So it has to wait for all the SSTables in the database to be compacted at the same time to release the disk space. So it has been, you can notice that ICS improved the space amplification by a large margin, because now we are able to provide the user with a predictable disk usage, no spikes and so on. So with major compaction, you can see that we remove the 2 times peak that happens with STCS.
Okay, thank you very much, Rafael. And on to the next slide, I would like to describe some future directions that we're exploring, and hopefully will be available in the coming months.
Okay, so now it's time to talk a little bit about the future directions for compaction strategies. I would like to say that some of the ideas here doesn't belong to just ICS. It could be applied to the other existing compaction strategies as well. So the first idea is adaptive ICS. This one we are actually going to apply only for ICS. This is the idea. Basically, the idea behind adaptive compaction strategy is to have a hybrid approach because ICS basically works with size tier. It has the size tier nature. So the idea is basically about using a hybrid approach where we are going to use the concept of behind size tiered and leveled depending on the workload. So basically, you can think that size tiered compaction strategy works only with size tiers, and leveled compaction strategy works just with levels. So the idea here is to use both approaches that would allow us to like optimize for space when we don't need to optimize for writes. So it's basically like trading off writes for space, write amplification for space amplification, depending on the workload. So we could use some machine learning approach, something we can like use some algorithm to see that depending on the workload of a specific table, we would like to tune the algorithm between size tiered and leveled approach for the ICS. And it could also, actually this idea could not apply to the existing compaction strategies. It applies only to ICS. And the second idea is the disk space controller. We have the CPU controller at the moment, and it was suggested that we could also have the disk space controller. Basically, the idea behind it is to like allow compaction to prioritize writes, prioritize compaction over writes when reaching capacity. It was noticed that in some of our tests, compaction falls behind, and as a result, we could end up running out of disk space because the write rate is more. We are ingesting more data than compaction can handle. So as a result, we can eventually end up running out of disk space. So the idea is to have a controller that would allow us to throttle writes on behalf of compaction. And we could, when it's an implementation detail, we could have like a high watermark. And it's good to mention that ICS could have a much lower watermark because it has a lower space amplification compared to STCS. So for ICS, we could have like 15%, and STCS would need a higher watermark because because it has a huge space amplification like Ben explained. And the last idea is to enhance metadata tracking. Right now, it was analyzed that sometimes we blindly select SSTables for compaction when it could happen that when, for example, let's say that we pick up two SSTables that barely overlap one another. That compaction actually would be mostly wasting computer resources. So the idea here is to enhance metadata in the SSTable that would allow us to predict how much disk space we are going to release when we compact a given set of SSTables. So the idea is to store metadata like cardinality information that would allow us compaction, to make more informed decisions on which SSTables could be compacted together instead of blindly choose SSTables based only on size, like size here. Size here basically blindly select SSTables that are similar in size, but there is no way to determine that the compaction is going to be efficient as a result of that selection.
All right. Thank you very much, Rafael.
That's it for now. I'm returning it to Benny.
Thank you. This was really fascinating, and I'm sure we'll have very interesting months coming up. And thank you all very much for attending the webinar. We will be taking your questions shortly. Before that, we would like to remind you that this series of Tech Talks is available to watch on demand on our website. And you are also invited to hear more about this subject at the upcoming Scylla Summit in San Francisco in November. We will have 2 full days of technical content, networking with Scylla engineers and also with your peers, plus a pre-summit training day that's highly recommended. All in all, the Scylla Summit is a great event. We hope to see you there. We'd like to take your live questions now. Please use the Q&A feature if you hasn't done that already. It's on the bottom of your console if you have any questions. And you also have our contact information on this slide to connect with us and continue the discussion offline. You're more than welcome to do so and stay in touch. Okay, I see we have quite a few questions logged in. Let's start with the first one. Michael asks if ICS has any impact on read performance, given it increases the number of SSTables. So the short answer is no, because we do use a Bloom filter to point us at the right SSTable when looking for read data. And just having more SSTables doesn't mean that we need to read more SSTables for a particular data item. Okay, then
I would also like to say that we use a data structure that has token, it's an interval map, and we are able to quickly look up SSTables because in ICS we split SSTables, the huge SSTables, into smaller SSTables, and interval map allows us to quickly look up SSTables based on the token range.
Thanks. Okay, the next question is very important. When can I try ICS? And when will it be generally available? So first, ICS is being heavily tested right now. We ironed the last wrinkles, and it's going to be ready in one of the upcoming enterprise releases. So hopefully within the next quarter, it will be generally available. If you would like to try ICS as a tech preview, please contact us offline and we can arrange some testing to happen using our testing branch if you would like to do so and get a sneak preview before everybody else. Okay, then we have a couple of similar questions about the workloads. What workloads are suitable for ICS? And we have an attendee asking, would this be preferable to the time-windowed compaction strategy for time series data? Rafael, can you please tell us a bit about what workloads are good for ICS?
Okay, so ICS follows the nature currently because we intended to make ICS work more like left compaction strategy depending on the workload. So in the future, ICS could also be a very good replacement for LCS when we apply the adaptive idea we have in mind. So because ICS follows the nature of STCS, right now it's a very good replacement, a drop-in replacement for STCS. And in the idea, it would be a very good replacement for left compaction strategy as well.
Thank you. So on to the next question. And just in general, we really appreciate these questions and your enthusiasm. These are great questions. So how much does ICS affect latency while ICS runs? And do we have any benchmarks for that? So we definitely benchmarked ICS versus STCS. And we in fact noticed no measurable difference in neither write or read latency comparing ICS to STCS. It has a very low overhead, and since it's compacting, each fragment by default is 1 gigabyte in size, the overhead is just unnoticeable. The next question is very similar. Is there any performance, throughput, or latency cost to the new ICS? And again, the short answer is no. We haven't seen any such cost to ICS. As for repair, is repair affected by ICS? Again, the answer is no. And just to explain the reason for that, it's not just magic. We need to remember that when we organize SSTables, big SSTables into SSTable runs, we take advantage that the outcome, the SSTable runs, contain an ordered set of SSTables where the SSTable fragments are disjoint one from the other. So they have no overlap and contain, they cannot contain any duplicate data. That means that for repair or for read or similar workloads, we need to read only the SSTable fragment that contains the read data. And we don't have to read any of the other SSTables because they are disjoint. Therefore, it has no impact on read or repair. Still need to read the data exactly once. The same way we would read it from the huge SSTables created by STCS. Okay, so we basically ran out of time and ran out of questions. Thank you very, very much, and see you all in the Scylla Summit in November. Thank you.
Thank you.